really what it is we're smelling is not sulfur, because it's not atomized sulfur atoms. It's actually sulfur atoms hooked onto hydrogen atoms to make H2S molecules. But we can smell it as sulfur. What we can do is realize that H2S is actually an acid. It's a sulfurous acid. So what we can do is put some baking soda in the fridge, in the kitchen, somewhere where these smells start to get produced from microbial action and breakdown. And when these acids start to rise up, they can interact with some of the baking soda, and they can neutralize that. And once that acid is neutralized into a salt, then it doesn't smell anymore, because it's locked everything up. It's turned it into a salt, right, and water vapor. So I mean, that's it. Magnesium hydroxide, which is milk of magnesia. Okay, you're actually putting in a base into your stomach to neutralize all that excessive stomach acid. All right, ammonium hydroxide. This is also called ammonia water. This stuff is potent. Okay, nasty stuff. Even though it says weak, that just means it doesn't dissociate very well. But as far as its ability to react, very strong. You'll use this in fertilizer, detergents, explosives. You use ammonia in the manufacture of like TNT and other explosives. You can, some interesting things about ammonia. You heard anhydrous ammonia, right? It's a big deal. You steal it to make your meth or whatever. Well, why? Because you can use this as a base as part of that chemical reaction, as part of a way to break down a certain point along that process. But anyways, you want anhydrous would be because there can be a little tail of water stuck to it. Anhydrous means it's in its purest form. There's no extra molecules tied up in it anywhere. You get more bang for your buck. Okay, it's more pure. But anyways, the reason it's sitting out there in those big tubes in the fields is because it is a fertilizer, because plants need a nitrogen source. And the thing about nature is they need a nitrogen source that can actually get taken up by their roots. And most nitrogen is atmospheric. It's gaseous. And it doesn't just go down in the soil by itself and get pushed down in and shoot up the roots as a gas. It doesn't do that. If you want to be able to get nitrogen atoms for plants to use, there's got to be chemical reactions that occur, and it's got to be able to lock that nitrogen up in various compounds and eventually make it water soluble, so it can soak down in the ground and get taken up by the roots. Okay, that's why ammonia is so nice, because this stuff falls apart pretty easily. Whenever this is sprayed and mixed in with water, you release a bunch of ammonium ions into the solution. They can get absorbed into the solution, go down into the soil, get taken up by the plants. Okay. All right. Also, you can make. Anybody watch Jericho, where they made ice from fertilizer? Anybody watch that? You don't watch Jericho, you need to. It's an awesome show. But you can take, when you dissolve this in water, it is a very, very endothermic reaction. It sucks in energy from the environment, and it makes right around it makes the area feel cold. Okay? So what you can actually do, I don't know how you could do it with just regular fertilizer. I don't know how it's concentrated enough. But if you have like anhydrous ammonia, you can do it. Take a bucket, bless you, wrap up and insulate that bucket so that none of the heat goes through the sides. Okay, so you've insulated it. Pour in your ammonia, and they used fertilizer because it has ammonium ions in it. Okay, so whatever, make a solution containing ammonium ions, and when it dissolves, what it will do is it'll start feeling really cold because it's sucking in energy from the environment. So when you feel it from the outside, you feel energy leaving you. Okay, so if you take a metal bowl and fill it with water on top, and fit that metal bowl right over the mouth of the bucket and insulate it all up, the only way that heat can leave and go into that system is through that metal bowl, right? You've insulated the outside. You've got a reaction happening inside the bucket that wants to draw in heat, pull it in from the environment, cool off the environment, in other words. So then you take water in a metal bowl, stick it on the mouth of the bucket, and the only place that heat can come from is from the atmosphere, and it has to travel through and into the water, and then it's going to end up sucking the heat out of that water and cooling off that water so cold to where it can actually freeze. So, kind of cool. All right. So the most common bases are going to be things that are hydroxide compounds. Okay, that's the giveaway. And some of them can be carbonates as well. It just depends. Okay, so they're going to react with hydrogen. Sometimes you can have an amine group, which is going to be a nitrogen and hydrogen, but don't worry about that. I don't think I'm going to ask you that, so it doesn't matter. All right, couple big theories in terms of how to describe acids and bases. We've got what's called the Arrhenius theory. We've got what's called the Bronsted-Lowry theory. Okay, what Arrhenius says, the first attempt at describing what these acids were, was that acids are a type of chemical. Well, I guess I'm starting with bases, I guess. Bases are, then, a type of chemical that will produce hydroxide ions and whatever cation it was stuck to in a solution. So when you drop it in there, like if you take solid sodium hydroxide, you drop it in water and dissolve it, you have put in a bunch of hydroxide ions and then some sort of other cation that was associated with it. So put hydroxide ions in, then you've got a base, if it does that. All right, so here's what I just said, that one. Now, what acids will do, according to Arrhenius, is ionize in water. In other words, they will dissociate, turn into ions, and they will separate out to produce hydrogen ions and some sort of anion, which makes sense. Okay, so you get something like this. Right? So the fact that hydroxides were produced makes it a base. The fact that hydrogens were produced here makes it an acid. All right, we always try to write the H for an acid in the front, not somewhere down the side. Okay, always pull that out because it's easier to keep track of. All right, so there's what you would get to visualize. Drop it in, it separates. Drop that in, it separates. That's what makes this a base. The hydroxides that are free. That's what makes this as an acid, the hydrogens that are free. Okay, so if we're looking at a chemical reaction, according to Arrhenius, we would see that the hydrogen from the acid is going to combine with the hydroxide from the base. And guess what happens when you take an H and another H and an O and put it together? You got H2O. You get water. Okay. So what might be helpful then, like I mentioned before, but especially in this chapter, to start thinking of water as this. Think of it as a hydrogen ion and a hydroxide ion coming together. Okay, so HOH. Now, what will then happen is realize that where did this hydrogen come from? Well, something was stuck to it, right? Some sort of negatively charged ion. This has something positively charged attracted to it. What will happen is its partner and this guy's partner will hook up and come together. That's what this says. The cation from the base, whatever was positively charged, combines with the anion over here from the acid that was stuck to it to make a salt. That's why I said acid plus base gives you salt and water. Okay? Take a look at hydrochloric acid and sodium hydroxide. H, OH, H2O. Cl, Na, NaCl. Okay, that's what happens when they come together. So the product, you could take something very dangerous, take hydrochloric acid. You could take something else that's very dangerous, sodium hydroxide, put them together, and then drink the solution when you're done, if you really wanted to, assuming that you could be comfortable in your math, that you've calculated things correctly, and you've neutralized everything that was there. Okay? So in theory, you could take muriatic acid. You could take, well, I would say you could take Drano, but there's other stuff in Drano, assuming Drano was just sodium hydroxide. Or lye, you could take a lye. You could take muriatic acid, you could take lye, both of which would burn your esophagus and maybe kill you. Mix them together in the right proportion, and you could drink the salt water that would be produced from that.